Hi, my name is Doug, and we're coming to you tonight from Emerald Hill Skies on the outskirts of Louisville, Kentucky. This is what we call an Emerald Hill Skies skylet. Now, with an Emerald Hill Skies skylet, what we're trying to do is examine something about the craft of astronomy, and especially we're trying to zero in on some kind of review or question regarding electronically assisted astronomy. So it's a little bit different than some of our normal live streams. But if you like this kind of content, we hope you'll subscribe and click that bell so you'll be notified. Maybe click a thumbs up if you like this kind of thing. And by all means, stop by and check out the live streams we've done before. About 200 different video live streams that are there in the library. And we'd like to just invite you to stop by and see those. But tonight, what we're doing is we're zeroing in on a question. And the question is, on a night like tonight, when we have 99% full moon, lots of illuminations for the moon, is electronically assisted astronomy capable of helping us see more than we would see with the human eye, unaided? I imagine you're probably already guessing that it might do that. But at the same time, I checked with a couple of other friends of mine, EAA practitioners, electronically assisted astronomers, and they had to admit they had never tried to observe something quite this close to the moonlight before. And so it's kind of a unique thing we're trying tonight. If you are going to log on live to the comments, we'd love to invite you to do so. We'll probably have just a little bit less interaction than normal. I see Gerard Joseph is there. I'd like to wish you good evening, Gerard Joseph. It is Palm Sunday, and happy Palm Sunday to you as well. We'll probably do just a little bit less interaction and go right to the practice. So let's get started, first of all, by looking at the sky. What we've done here is we've stopped down the camera that we're using for this image, which is a ZWO-ASI 178 monochrome Pro. And this camera has an all-sky lens of about 153 degrees, something like that. Pretty much similar to what the eye would see. So in this picture, you can see the Big Dipper perhaps, barely over here on the left. And if you look at the back two pointer stars, those back two pointer stars point directly to our targets, which are Messier 95, 96, and 105. Now these aren't necessarily the brightest of all Messier objects. They're about magnitude 10.6, 10.1, and 10.5 respectively. So not that bright, certainly not naked eye bright. You might be able to make out the nebula right here and Regulus right here. So this is the constellation Leo, and you probably recognize, those of you who are familiar with trying to find Messier 95, 96, and 105, you can pretty much follow the pointer stars backwards. And once you've passed through Leo, you can almost look at it as a right triangle to be able to find these targets. Look at what that does. Maybe not quite a right triangle, but what that does is puts us right close to the moon. So now let's go to our Planetarium software and let's see this in real life. So let's see, here's Ursa Major, Big Dipper. We follow the two bull stars at a backwards and look at the nebula and Regulus, and pretty much isosceles triangle right in between them is where our targets are located. So let's go back to live again. So our targets are right here. And I've got the AstroPlanner queued up here, so I can tell you that the distance to the moon is said to be 13 degrees. Now, who in their right mind would try to observe targets like this with a 99% illuminated moon within 13 degrees of the moon? In fact, I have AstroPlanner set up to warn me if we are within 20 degrees of the moon. But I just thought this would be an interesting study. So I asked a friend of mine who is a bit of a scientist in a way. He did programming for a living. And I asked him about this, and boy, he deep dove right down into it. he says that I don't think I've ever tried to observe galaxies 8 degrees from a full moon, or 10 in this case, 13 degrees from a full moon in this case. He said, I wonder if we can be somewhat scientific about this and compare the surface brightness of the sky with the surface brightness of the object. The image below shows the sky brightness in magnitude per square arc seconds. The image on the left is a new moon, and the image on the right is Saturday night, as this live stream is being recorded at his location, near midnight. He says the surface brightness of the sky on Saturday is around 18 magnitude per square arc second. And he says that these objects are right around 22.3 mag per square arc second. Now, the one he used was M66 for his study, but it has a magnitude of 9.7. And the three objects we're looking at right now have a magnitude of 10.6, 10.1, 10.5, so almost exactly the same. So he says he did come across a Sky and Telescope article that talks about sky glow and the moon. And it's called, How Does the Moon's Phase Affect the Sky Glow of Any Given Location? And how many days before or after a new moon is a dark site not compromised? He says the article talks about a sky glow of 18 magnitude per square arc second for a full moon. However, you are really, really close to the moon, so like 10 degrees. But for now, let's say it's 18 magnitude per square arc second. So then he found a spreadsheet on the RASA website. What does that stand for? Royal Astronomical Society of Canada, maybe? Surface brightness versus magnitude. It's the RASA Vancouver, and that's at rask-vancouver.com. And it tries to calculate the visibility of an object visually based on surface brightness. He said he had to alter the spreadsheet since it didn't support such a bright sky, even though the spreadsheet says the sky brightness is 19 magnitude per square arc second. He changed the lookup table to roughly approximate 18 magnitude per square arc seconds. And when he got all done with this, and you can see the spreadsheet down here at the bottom, the little tool that he found at the RASC site, which takes into consideration the diameter of the telescope, the F ratio, the magnification, the sky brightness, the objects, and then he tries to simulate what the camera would see using a ZWO-ASI 2600 MC Pro, which is what we're using. And when he gets all done, he basically finds here that the answer was a big, bold maybe. And he kind of laughed. He says it's this momentous result, maybe. He says, we know the sky glow will be less than 18, getting brighter, but we also know that you're using an awesome camera, scope, and stacking software. So he says he thinks we should boldly give it a try. And he said it would be a fun experiment. So then he says, well, after all is said and done, he gets this maybe. He wonders if maybe he should remove the word scientific, because this now becomes more of a guess. And this is his model over here of the sky glow that's going on. So as you can see, obviously, the sky has drastically changed. And we can see that with one glance at this screen. There's just so much sky glow within 20 degrees of this moon that's hardly worth even trying it. But for the sake of trial, let's go now to our live view, and that's in SharpCap Pro. And here we are. This is a live view of the sky. Now, I'll tell you what I've had to do. I've had to bring up the black level threshold so much to be able to kind of cancel out all that glow. So imagine if you're accustomed to SharpCap, we've brought up the black level so that we basically said to SharpCap, I don't care what you think. We want you to establish a new baseline of approximately 18 magnitude per square arc second. That's going to be our definition of black. So the software is like saluting us and just kind of robotically saying, okay, if that's what you want, it doesn't make sense, but I'll try it. So SharpCap is looking at a definition of black that approximates a really bright sky. Now this mid-level, let's zoom in, and of course this would be M95 right here, M96 right here, and M105 here. M95, M96, and M105. So let's zoom in first on M96. Now first of all, I think it's amazing just that we can even see anything. We're zoomed in at about 170% here. I don't know whether you are able to see it where you are, but we're basically looking at the same screen. We can even tell of this galaxy, M96, that it is slightly barred. Now this is 31 million light years away, and of course it was discovered by Pier-Tech around 1781. It's categorized as a double-barred spiral. Now I think we're only able to see one bar. Now we're into the pixels of the camera, see? We're only able to see one bar, but we could detect that bar before we even read about it. It has a small inner bulge through the core, along with an outer bulge, about the same mass and size as the Milky Way. It's a very asymmetric galaxy. Its dust and gas are unevenly spread throughout its weak spiral arms. Now, I don't know if you can see the spiral arms. Let's bring up our mids a little more, see if we can make those spiral arms pop a little more. Right around there, we're seeing spirals out here, and sure enough, look at this funny spiral here that looks like it's a little bit farther away than it should be. Its core is offset from the midpoint of its extremes. Its arms are asymmetrical, both since they're thought to have been influenced by the gravitational pull of other galaxies within its group. Stop and think about what you're doing here. Just pause for a moment. You're observing an object that is said to be, I want to make sure I'm on the right line, M96, 31.31 million light years away, with a magnitude of 10.1. And you're observing it when it is just 13 degrees away from the 99% illuminated full moon. Now I think M95 is going to be a little more of a challenge. Let's go up and find it. So here's M95. But keep in mind, M95 is pretty much spheroidal anyway. Let's look at M95 here. A barred spiral galaxy about 33 million light years away in the zodiac constellation Leo, discovered by Pier-Tech in 1781. There's not a lot to see here anyway. We can try to turn up the mids a little bit more, but that's basically all we're going to see. But we can see that it's different than a star. So yeah, I'll admit, the kind of observing is definitely going to be changed. But look at this view of M96. Dare I say that's even kind of amazing that we can see that. Now what we're doing here is we're using 20-second exposures with a gain of 100. And while I've been doing the video, I admit, I've been trying to get the video queued up and doing the title screen and all that. So this is at 28 minutes. So what we've done is we've zoomed in on an object that is within 13 degrees of the full moon. Now here is M105, and it's an elliptical galaxy, which you know what elliptical means. Basically, it has very little structure that we can see. It's basically a blob. It's 36.6 million light years away in the equatorial constellation Leo. It's the biggest elliptical galaxy in the Messier catalog that is not in the Virgo cluster. It was discovered by Pierre-Mechien, 1781. It's one of a few not object verified by Messier, so it was omitted in the additions to the catalog of his era. It was appended when Helen Hogg found a letter by Mechien locating and describing the object which matched those aspects of its first published name, NGC 3379, known to have been a supermassive black hole at its core. What's amazing here is that you're seeing this just 13 degrees away from the full moon, 99% illuminated full moon, which I think is just radical. Now, recently I've been playing with the software SkyTools 4, and I want to be honest with you. SkyTools 4 sort of like imposes its will on you, saying, don't even try to observe these things because it's worthless. It's too close to the moon. The background glow is going to be too bright. But I also want to tell you that I've worked and worked with SkyTools 4, and our RASA 11 is just 11-inch aperture. To approximate, and I'm just talking about approximate, to approximate what our 11-inch RASA can see and do with the night sky, just even to get close to it. With SkyTools 4, I have to use, and this is with the developer's input, I dialogued back and forth with him. His name is Greg. People on his forum, we dialogued quite a bit, and they guided me through this process. With guidance from the developer, I had to configure our Celestron RASA 11-inch as if it were a 32-inch telescope. What's more, I had to cheat all kinds of ways at the way that it had the f-stop and the field of view and the focal length in ways that are just beyond. You couldn't make a telescope like this. A 32-inch telescope like this just doesn't exist. But that's the way I had to configure an 11-inch RASA to be able to represent what we might see visually if we were able to use it. And even then, it's an impossibility. And SkyTools 4 says, don't even try it. Why am I sharing this with you? Well, in the first place, I'm saying, if electronically assisted astronomy can do this just 13 degrees away from a 99% full moon, if you were to look visually through your eyepiece, all you would see is glare. Glare. If electronically assisted astronomy can do this, imagine what it can do on a moonless night with the object of your choice. So that's what this skylit is all about. It's kind of a demo. We actually are seeing structure here. Now you can see at the point that I've got this dialed up, we're seeing a little bit of halo here on the left side of the screen. That's because we've defined the black level so close to the glare that we're even with that black level defined so close to the glare, we're still seeing a little halo. But look at this object now. We're actually seeing that bar. And this is M96. Now, just to make sure you understand that I'm not fibbing, these are the real objects. Let me turn on SharpCap's Deep Sky Image Annotation so you can see that really is M96, that really is M95, and this really is M105. These objects that we've been looking at, sure enough, are the real thing. I'm not at all faking this for you. What I'd like to suggest is electronically assisted astronomy, EAA, rocks. On this channel, we kind of make it a matter of principle that we don't quit, even on moonlit nights. Because why? Part of the reason is because EAA still works, even on a moonlit night. If you are still using an eyepiece, no problem. That's great. Please feel free. We congratulate you and we encourage you to keep on doing that part of the hobby. But if you've ever wondered how to make your 11-inch telescope feel like it was a 32-inch, try EAA. We think you'll like it. Well, that's all we're going to do tonight in this Skylit. Thanks for joining us. And if you're watching this in a recorded version, again, if you like content like this, please subscribe and click that bell so you'll be notified when we do broadcasts like this, live streams. And if you want to, only if you want to, click the thumbs up. It doesn't cost you anything, but it does help the channel to grow and can get in the hands of more people just like you. Thanks a lot for watching. I'm sorry we didn't do as much audience interaction on this Emerald Hill Skies Skylit, but we'll be back next time with a normal live stream and building this Emerald Hill Skies community as we have all along. Thanks to you who did